So now that we know the different pieces of a hypothesis test from the last lesson, we need to start putting it together. So in this lesson, we're going to learn how to test a claim about a proportion. So we're going to look at the whole procedure of how to do it. We're going to do it with p-values. We'll do it with critical values. We can even do it with confidence intervals as well. We're actually not going to focus too much on that because we've already covered confidence intervals. But we're going to be focusing on proportions. So some notation that we should already know, things we're going to need in order to provide to perform a hypothesis test would be we need to know the sample size. N represents the sample size. P represents the population proportion. That's basically the idea. That's what we're going to be trying to test, some claim about the population proportion. P hat's the sample proportion, sometimes given, sometimes we have to actually calculate it. And Q is just a complement of P, so 1 minus P. So in order to do a hypothesis test as it relates to proportion, there will be 3 requirements. We've already talked a little bit about this when it comes to the N times P and N times Q. So sample observations have to be a simple random sample. The basic idea is all the information we're collecting from a sample should be done properly. Our sample should be a simple random sample, a well-collected sample. The next thing we need is conditions of a binomial distribution have to be satisfied. Binomial distribution essentially requires to have a few things here. One, you have to have a fixed number of trials. Trials are independent. Each trial is in 2 different categories, success or failure. The probability of success remains the same in all trials. We need this along with step 3, which is N times P greater than 5, N times Q greater than 5, basically so that we can start to draw the normal distribution. Okay, this is the important part. We need the binomial distribution and N times P and N times Q so that we can draw our normal curve, our bell curve. And so, we're going to look at all these things. They're going to end up being satisfied in here. These are pretty simple. Fixed number of trials basically means that your sample is a fixed sample. Each trial is independent. Each individual data value in your sample is not dependent on another data value. That's important. Each trial is 2 categories, success or failure. So you broke your outcomes of what you were looking for into 2 groups, success or failure. What you were looking for is the success and everything else is your failure. And the probability of success remains the same. So your probabilities are consistent throughout your entire sample. We already talked about our test statistic for proportion would be a z-score. It'll be a z-score based off of this formula, p hat minus p over the square root of p times q over n. This, again, we've already practiced calculating the test statistic. This will be the specific one we use for proportion. It's a z-score. That's the most important part. We will either use p-values or critical values. Either one, it doesn't matter which one we do. We'll be doing it based off of the normal distribution. So we're going to be using the z-score table to either find p-values or areas. Critical values are z-scores, okay? We can use the table that we've been working with for z-scores to do both. We'll see how to do both of them in a full hypothesis test. And you're going to see it's basically asking you to do much of the same thing. Just do you want to look at it more in terms of areas or do you look at it more in terms of the z-scores that bound them? So remember, regardless of what method we use, the p-value method or the critical value method, we have to decide to reject or fail to reject 8 sub 0. This is the p-value method. If the p-value method is less than or equal to alpha, we reject. If it's greater than alpha, we fail to reject. In the critical value method, we decide whether or not the test statistic is in or out of the critical region. Test statistic in the critical region, reject. Test statistic not in the critical region, fail to reject. Again, I'll show you that these are really the same thing, okay? We'll look at it in a given problem. We'll see that these are generally stating the same thing. This is comparing areas. This is comparing z-scores. After we get to that point, we get our final answer. We follow this flow chart. Does the original claim contain a condition of equality? Yes or no? Did we reject 8 sub 0? Found in this step here, depending on which one we did. But we would get an answer. Yes, we rejected. No, we failed to reject. Okay? and then we end up in one of these four boxes. First box is where we actually support the claim. First box is where we actually reject the claim. Okay? Third box is where we actually support the claim. Second box, fourth box, nothing's really being said here. There's not enough evidence to really give an answer is what those two boxes are saying. So here we go. Let's do an example. A teacher believes that 85% of students in class will want to go on a field trip to the local zoo. So she wants to perform a hypothesis test to determine if the percentage is the same or different from 85%. So the teacher samples 50 students and 39 reply that they want to go to the zoo. We're going to perform a hypothesis test. We're going to use 1% significance level. So what we're going to do is we're going to first write our original claim. She wants to test the claim that the percentage is the same or different than 85%. So let's clear that up. Let's say it's different from 85%. Okay? So we're going to test the claim. The original claim is that the proportion is not equal to 85%. Okay? Or we could write that as 0.85. Okay? Remember, we should probably write it as a decimal when we're talking about it in terms of proportion. So I'll go 0.85. So that's the original claim. The opposite would then P equals 0.85. H sub 1 would be that P does not equal 0.85. Remember, you find that by doing what? You look at these two statements here. Which one does not have the equality in it? Which one has the less than, greater than, or not equal to? That's the first one. And H sub 0 is always that P equals 0.85. From there, this automatically tells us we have a two-tailed test. Okay, now we got to gather some more information here. From the sample, we know the sample size is 50. We know that the sample proportion of people who want to go to the zoo is 39 out of the 50. Okay. And we know our significance level is 1%, 0.01. Okay. So what we're going to do is next we're going to find the test statistic. So it's a z-score. It's p hat, which is 39 over 50, minus p, which is taken from h sub 0, 0.85, over the square root of p, 0.85, times q. Remember, q is the complement. So if p is 0.85, q is 0.15. Okay? Over the sample size, which was 50. So we calculate our z-score and we get negative 1.39 when I round the two decimal places, because the z-score should be two decimal places. Okay, so now what am I going to do? I'm going to decide what way I'm going to go about solving the rest of this. So I'm going to just, for the sake of doing it, I'm going to say let's do the p-value method. There's really no reason why I'm choosing this, just because. Choose the p-value method. In the p-value method, what I'm going to do is I'm going to draw my picture. Based off of h sub 1, it says I should have a two-tailed test. In my two-tailed test, these two areas combined are my p-value. The test statistic is this value right here that separates the p-value from everything else. It's a symmetric picture since there's two tails. This is a z-score of negative 1.39. So this should be a z-score of positive 1.39. And what's the combined area in the two tails? Well, I can look up the area in my table of z-scores. I can find that area and I will get for this area down here, it should be 0.0823, which means this is also 0.0823. 2, 3. So the p-value is the combined area. So the p-value will be double that. So I'm going to get 0.1646. That's my p-value. So the next step is to compare the p-value to alpha. Alpha, remember, was 0.01. So if we look at these two numbers, which one's bigger? Clearly, the p-value is bigger than alpha. Okay? And that's going to lead us through the rest of the problem. So remember, look at what we had to do. This said if we do the p-value method and the p-value is bigger than alpha, we should fail to reject h sub 0. So now we start our process to get our final answer. Does the original claim contain an equality? The original claim, if you remember, was that p does not equal 0.5. Okay? So does that contain a condition of equality? The answer would be no. It's a not equal to. So we go down to here. Okay? Do you reject h sub 0? No, we failed to reject because the p-value is bigger. So where do we end up? We ended up right here. There is not sufficient sample evidence to support the claim that our claim was that the proportion is not equal to 0.5. Okay? That the amount of kids that want to go on the trip is not 50%. So what does that tell us? Well, what that would tell us would be if we ended up in this box, not a whole lot, right? There's not enough evidence to support that claim. Doesn't mean we're rejecting it. We're just saying there's not enough evidence to support it. So what would we do? Well, we could go back and do a new sample, ask some more kids whether they want to go to the zoo. We could change our claim. Remember, we could have done equal to 0.5 instead of not equal to 0.5. We did not equal to 0.5. That could change things because that would change some of the answers to these questions. And so what you see, though, is this is the formal process for completing a hypothesis test if we did the p-value method. Now, let's just say I did the critical value method. I would end up in the same spot, that I would fail to reject h sub 0. And I'll show you real quick how that would be. We would still have a two-tailed test, but instead of calling these tails the p-value, I'm going to call these two tails the critical region. Okay? And the critical region is defined by alpha. So alpha is 0.01 stated in the problem. What we would need to do is find what z-score we had here and here, separating the critical region from everything else. Well, we would have to look at our table. In our table, if we know that the combined area between this area and this area is 0.01, then we know each one individually is 0.005, half of 0.01. I would look up 0.005 in my z-score table and find out that the z-score is negative 2.575, and over here it's positive 2.575. And then what I'll do is I'll look to decide, is my test statistic in or out of the critical region? Well, my test statistic was negative 1.39, I believe it was, negative 1.39. Which is not in the critical region. This is the cutoff. This is the z-score that is the cutoff of the critical region. It's not in there. And since it's not in the critical region, we fail to reject. So we end up in the same spot. Now, listen, this is doing the same thing. Over here, we said the p-value is bigger than alpha. The p-value is the area bounded by the test statistic. This is your test statistic. This is where it sits. Of course, this area is going to be bigger than the critical region's area because of where the test statistic falls. Since the test statistic is not in the critical region, the p-value would be bigger than alpha. So I'm trying to tell you that these two things are saying the same thing. This is doing it in terms of comparing the areas, and this is doing it by comparing this z-score to this z-score as our test statistic. But you can compare the two z-scores here, or you can compare the two areas that they bound. Either way, you end up in the same spot, and then end up with the same position here that we failed to reject, and we don't get much of an answer. Let's do another one. Okay, so let's do another hypothesis test for proportion. So according to the February 2008 Federal Trade Commission report on consumer fraud and identity theft, 23% of all complaints in 2007 were for identity theft. In that year, Arkansas had 1,601 complaints of identity theft out of 3,482 consumer complaints. Does this data provide enough evidence to show that Arkansas had a higher proportion of identity theft than 23%, test at 5% level? Now let's look at it. So as far as the proportion from the sample from Arkansas, so the sample proportion, 1,601 complaints out of the 3,482. If I do that computation, I get 0.46, okay? 0.46, which is 46%. So from this sample, 46% of all the complaints were for identity theft. So what they're saying is that enough to show that Arkansas has a higher identity theft than the 23% which was found in the 2008 Federal Trade Commission? So the claim is that the proportion from the whole population is greater than 23%, so 0.23. That's our original claim. And we want to use this sample evidence to decide whether or not if that's going to show that it's true. So our sample size was 3,482. Our alpha is 5%, 0.05. And that's all the information we can get out of this thing. So let's start going through our hypothesis test. So what we need to do is write the opposite of our claim. So the opposite is that the proportion is less than or equal to 0.23. Then we find our H1 and our H0. Okay. H1 says which one of these two does not contain inequality. So that's this one right here. So that's going to be the proportion is greater than 0.23. And H sub 0 is always that we're equal to the claimed value, so equal to 0.23. So once we have that, this is going to tell us what type of test we're going to be working with through this problem. In this case, we're going to have a left-tailed test, okay? Actually, sorry, no. no, that's not what that says. That says we're going to have it's greater than, so it's going to be a right-tailed test. I got to make sure I can tell my left from my right. So that's my right-tailed test. Okay, greater than. After we get to this point, the next thing we want to do is find our test statistic. So our test statistic, in this case, will be a z-score. Okay? And we're going to use our p-hat, 0.46, minus our p, which is 0.23, divided by the square root of p, 0.23, times q. Well, if p is 0.23, right, q is always 1 minus p, so this will be 0.77, okay, over the sample size, which was 3,482, okay? So once we calculate that test statistic, then we can decide what method we want to do, whether it's the p-value method or the traditional critical value method. So I get a z-score for the test statistic to be 32.26. Now that seems a little unusual because it's so big. Our z-scores typically are not 32. I mean, we're talking 1, 2, 3 at the biggest. 32. Now, it's not wrong. This is the correct test statistic, but the question is, why is it so big? Well, it's because our sample proportion is so far off from our claimed value. So we're very, very unusual, very far from the center. I mean, this is pretty extreme. And so that's why we got that value. All right. So then the next thing we want to do is say, all right, well, let's decide which way we want to do this. And I'm going to do it two ways. I'm going to do it with the p-value method, so you see what kind of answer we get. And then I'm going to do it with the traditional, the critical value method, and you see we'll get the same answer. So let's do the p-value method first. Okay? So in the p-value method, we have to decide what type of test we have. Again, we said it's going to be a right-tail test. Okay? This area here is our p-value. And what we need to do is we need to find what that is. Well, how do we find it? Well, this value right here that separates this area from everything else is this test statistic here. This is the z-score of 32.26. Okay? So that critical value, okay, that test statistic is going to determine what this area is. So if we look at this z-score in our z-score table and find the area to the left, then we can do 1 minus the area to the left to find the area to the right. Well, this z-score is so big. If you look it up in your z-score table, it only goes up to 3.5. We've used that z-score table enough. You should know it only goes up to 3.5. And anything bigger than 3.5, it says the area to the left is going to be 0.9999. So this is going to be 1 minus 0.9999. So the p-value here is 0.0001. That's our p-value. And so what we have to do is we have to compare our p-value to our alpha. That's how the p-value method works. So clearly alpha is bigger than the p-value. All right? And that will lead us through this problem. That's one way to do it. Another way to do it is with the critical value method, which will basically give us the exact same thing. So we draw the picture again. Okay. It's a right-tail test. But instead of calling this area the p-value, this area is going to be alpha. This is going to be our rejection region. We'll call that. And so this was 0.05. And so what I can do is I can say if my area is 0.05 to the right, then this would be 0.95. And I can figure out what z-score this is that separates this area from this area by using my table of my z-scores. And then once I have that, what I'm going to determine is my test statistic going to be inside the critical region? So is my test statistic here, or is my test statistic here? Okay, based off of where this cutoff is for what we call the critical region. Okay, so if I use my z-score table, I can look it up, and I'm going to find out that this z-score is 1.645. It's one of those special ones with the star that leads you to the area of 0.95 to the left. So anyway, that's it. Remember, my test statistic was 32.45. It doesn't really matter what the decimal is. 32. Clearly, it's over here. It's in the critical region. So if my test statistic is in the critical region, right, that's the same thing as saying that the area bounded by the test statistic, which we call the p-value, is smaller than the area bounded by this value, essentially alpha. So this is what I'm trying to tell you, is that this is the same thing we just did a second ago. Here I'm comparing these z-scores. In the p-value method, we were comparing this red area to the blue area, which is alpha. This is the p-value. All right, either way, we're getting the same thing. So we got to finish this problem off. So if we did the p-value method, we decide whether or not the p-value is bigger or smaller than alpha. The p-value is definitely smaller than alpha, so we reject h sub 0. In the critical value method, if the test statistic is in the critical region, which it was, we reject h sub 0. So either way, we get to that point where we reject h sub 0. So then we start this off. Does the original claim contain inequality? The original claim was that p is greater than 0.23. Does that have an equality in it? No. Let's go to here. Did we reject H sub 0? Yes, we rejected H sub 0. In either case, we didn't have to do both, but we did both. Yes, we rejected H sub 0. So here's our final answer. The sample data supports the claim that, and the claim was that the proportion is bigger than 0.23. Okay? Remember, this is the only one where we actually support the claim. And think about it. Our sample proportion, the amount of people from Arkansas that filed claims, okay, was 46%, 0.46, okay, 46%. They were saying, is that big enough to say that it's bigger, that the proportion is bigger than 23%, 0.23? Well, yeah, that's pretty big. That's a big gap. It's twice as much, right? Twice 23% is 46%. So I would say that that sample data definitely should support the claim that the proportion is bigger than 0.23 or 23%. And that's why we arrived at this box, because this was so extreme compared to the claim value. If the sample proportion was, I don't know, let's say 24%, right, instead of 46%, it was really close to the claim value. We might not be far enough away to get to this final answer. Maybe we get into this one where there's not enough evidence to support the claim because it's so close. But because this was so extreme, we were able to get to the point where we say, yeah, this evidence definitely should support the claim that we're bigger than 23% in Arkansas.